Okay, we move on to Cesar, who's going to tell us about Rényi entropies in the n goes to zero limit.
Okay, thank you very much. Okay, thanks everyone for coming, and let me start by thanking the organizers for letting me speak today and for organizing this very nice conference. So today I'm going to try to, be brief and tell you a little bit about Rényi entropies, entanglement temperatures, and how these two concepts can be realized explicitly in the context of holography. Rényi entropies in particular, we are going to be interested in this really unexplored limit when the Rényi parameter goes to zero. This is partly work based on this paper that was in collaboration with Horacio Cassini and Pedro Martinez, Horacio at Centro Atómico and Pedro at the Universidad de La Plata. And the forthcoming work is going to be also in collaboration with Gonzalo Toroa. Okay, so the outline is kind of trivial. I'm going to try to explain you what entanglement temperatures are. Then I'm going to explain the relation between entanglement temperatures and the Rényi entropies, in particular in this kind of interesting limit when the Rényi parameter is small. And then I'm going to show you a particular example in which I can realize this relation concretely in holography. The example is going to be two-dimensional CFTs. And then I'm just going to end up. Okay, so as a brief summary of the topic of today's talk, let me just motivate the idea that, if in a lab you only have access to a particular subregion of a space-time, then the best description, at least from the perspective of quantum mechanics, is to use density matrices. Density matrices that you obtain when you trace out everything that you don't know, that you are agnostic to. Okay, this is very well known, but in quantum field theory, this is not well defined, but for the purpose of today's talk, I'm just going to assume that it is. And for the ones who don't like that idea, then let's just think about putting in a cutoff in the field theory. So everything is finite dimensional, and then at the end, you can remove the cutoff by being careful how to do it. Formally, you can write this density operator, which is completely positive and so on, as the exponential of some Hermitian operator, which is precisely what is known as Mulder-Hamiltonian. And this operator actually allows you to describe that state, the state that reduced to this, in a unitary fashion in all the causal development of the associated spatial region. So you can have a complete description of this region, this causally complete region if you want. And they also introduce some natural notion of time evolution, which is precisely the one obtained by this unitary. Okay, so there are many quantities that you can compute with this density operator. In particular, there are some quantities that are related to the amount of entanglement that the original state has with respect to this bipartition. And so one of those quantities are precisely the Rényi entropies. So Rényi entropies are just logs of traces of integer powers of the reduced density operator, if you want. And importantly, these simple numbers has a lot of information about the original state, the reduced state. How you can see this explicitly in this equation, essentially. So if you know all the Rényi entropies, if you invert this equation, basically you can know about the distribution of eigenvalues of the reduced state. And that's very fine-grained information. Now, these Rényi entropies in the literature has been always used, mostly used just as an intermediate trick in order to get access to the most interesting von Neumann entropy of the reduced state, just by taking this formally this limit n going to 1. But today I'm going to talk about these guys and some notion of temperature that I hopefully will introduce next. Okay, so there is this notion of temperature. This is the Unruh temperature. But let me just emphasize that in general, this Mulder-Hamiltonian is a highly non-local operator, but there are some particular cases in which you actually know exactly what this operator is. And one of these very rare cases is precisely the case of the Rindler wedge. So if you just consider half space and the causal completion, which is the Rindler geometry, then the Mulder-Hamiltonian generates is a local operator whose unitary generate these integral curves, which can be associated to observers that have constant accelerations. And it's very well known the fact that for these observers, or these observers feel or can measure a temperature, which is precisely this notion of Unruh temperature. So now, from this perspective, from the perspective of this effective description of the reduced state, which is given by the Mulder-Hamiltonian, you can see that the Unruh temperature is essentially just given by the kernel of this operator with respect to the density energy, in some sense. But this is very, very constrained to the Unruh case or to the Rindler geometry. So the idea was, how can we extend this pictorial idea to arbitrary regions? If there is a way to assign some sort of notion of temperature, also for regions that are not necessarily just half spaces. And this problem was attacked by this group of people in 2017, and they have a concrete and very elegant answer to that question. So the idea that they propose is to consider a very well-defined in quantum field theory quantity, which is precisely this relative entropy. So the relative entropy, for the ones of you who are not very familiar with, is just a very robust measure of distance between states. It's positive definite, it has some monotonicity properties, a very interesting quantity. You can write it in terms of like difference of expectation values of the modular operator and differences of the von Neumann entropies. And what they considered was the following experiment. Let us consider the difference between two states, but let us pick a very particular state. So let's say if you consider your reference state as your ground state, let us consider a state that is obtained from the ground state by acting with a unitary. And that unitary is going to create a bunch of energy that is very well localized both in space and momentum. So this is the picture that I have here. I pick a point and I try to create as localized as possible some unitary that represents this bunch of energy acted on the ground state. Okay? And now I compute the relative entropy between these two states. What these authors realize is that this relative entropy actually scales linearly with the energy that is included by this unitary. And you can see from this relation that basically because you have a unitary, then the change in the von Neumann entropy is just zero. And then what you are really probing here in this quantity is just the expectation value of the modular Hamiltonian in this excited state. So this definition actually agrees immediately with the picture that we have here. If you compute the expectation value, you will get precisely this coefficient. So the notion of entanglement temperature is just this proportionality coefficient between the relative entropy and the energy. Yes, please.
Small energy or large energy?
This is only for very large energies. Yes, yes. So it's very localized both in space and momentum. So this is a asymptotic statement. Okay, so this is a very nice feature. However, let me just make a remark here. This notion of temperature is kind of strange because it not only depends on the position, but also depends on the direction in which you perturb the state. So it's a space and momentum dependent. Okay, let me move a little bit forward. So the idea now is how can we compute this object? It seems to be very interesting. It gives us a measure of distance and it seems to have some thermal properties and somehow codifies some thermal properties. And actually from this formula and the relation with the modular Hamiltonian, basically this local temperature is giving you something about the local structure of the modular Hamiltonian. So it has very fine-grained information about the modular Hamiltonian, which as I motivated before is a very important object in quantum field theory. Okay, but how we compute this thing? So what I would like to tell you next is that the same authors found a very complicated way to get access to that information. And that information is kind of geometric in some sense. So it's very interesting. But of course, they were only able to do that very precisely in the case of free theories. Okay, so everything here is for free theories. So for a free quantum field theory, then it is well known that you can diagonalize explicitly the modular Hamiltonian in terms of linear combination of the field operators, phi and the conjugate momenta. So this is, let's say, in the diagonal form. And so the problem that they consider is, okay, since we are just exploring the modular Hamiltonian, this very high energy regime, then let us try to solve this problem in the case in which the modular energies are very large. And it turns out that in this limit, you can actually argue or you can obtain an approximate expression for this modular Hamiltonian that I'm going to call it high E for high energy approximation of the modular Hamiltonian in terms of creation annihilation operators, where these operators are basically creating creating wave packets that are localized both in momentum space without violating the Heisenberg uncertainty principle and so on. And explicitly, the kernel that appears here is going to be precisely the entanglement temperatures. So far, I haven't said anything. I just said that you can write this formula by doing some manipulations. But of course, when you do all those manipulations that allow you to get from this point to this point, then you have to tell me how to compute these kernels. And that's what they did. This is a little bit technical, so let me just tell you what the answer is. So the answer or the problem that you have to solve is this set of equations that there are some sort of iconal equations because you can take it just an infinite limit of some wave equations that you have to solve. But then the information is encoded in these vector fields. And the problem is the following. So you start with the region here at t equals 0. You extend it in Euclidean time. So this is the Euclidean version of this original or the original setup. And then you ask yourself to find all the set of solutions of vector fields which have equal magnitude They are mutually orthogonal everywhere, and they have this particular circulation. So B doesn't have circulation at all with respect to any closed loop, but A has this particular circulation provided this curve circles the boundary of the region B. So these are the boundary conditions that you have to impose. Actually, there is an extra boundary condition, and it's the boundary condition at the t equals 0 slice. That is when you put the region. And the boundary condition is that the vectors B has to be parallel to the t equals 0 slice. Therefore, the vector A is orthogonal. So these are basically the setup. You solve for all these type of vector fields, and then given one solution, then for a given point, you will find the local temperature associated to that point, and for a momentum that has the same direction that the direction of the vector field B. And then the local temperature is just related to the magnitude of that vector field B. So this, I'm just giving you a prescription. This is, of course, not a derivation whatsoever. But by solving this purely geometric problem, you will get all the information that you need to get access to the high energy approximation of the molar Hamiltonian. This is the message of this slice. Okay. So just to give you very briefly an example so that you see that these equations are not so exotic. In 2 dimensions, these equations are actually just the Cauchy-Riemann equations. So actually you know already what is the most general solution. The most general solution in 2 dimensions for an arbitrary number of intervals is just given by an analytic function with some monodromy conditions that are satisfied by a simple log function. So we know already the solution for an arbitrary number of intervals. So it's very simple, it's very elegant, and very nice. And actually this gives us a motivation to conjecture that this solution will be valid for any theory, not only a free theory, but for any CFT. So for any CFT, if you ask for the local temperatures, they will be universal because of the symmetries of the problem, and then you already know what the local temperatures are. You just use this prescription and you have the local temperatures. And just for illustration purposes, I illustrate here the case of one interval. So the vectors A and B, the vectors A will be like the integral curves of the vector B will be the circles that are orthogonal on the interval in this point, and the B's will be the other set of integral curves or level set functions if you want. Okay, so this is the particular realization of this iconal problem. Okay, let me move a little bit forward because everything I have told you so far, in particular the data that I described for you, is only for the t equals 0 slice. However, I told you the molar Hamiltonian is interesting because it allows you to study or to complete your system in the causal development of that region. Therefore, it will be also very interesting to be able to write this operator on any Cauchy slice, which is homologous to the Cauchy slice B, or to the surface B. And in order to do that, this is very interesting. You will see why it is going to be so important. In order to do that, then basically you need to extend the iconal problem into Minkowski signature. And this is what we did in our first paper. So, and I'm just going once again to describe how the extension goes. So the extension is the following. You basically use the Euclidean setup, the Euclidean problem, in order to get the local temperatures at the t equals 0 slice. And you take that information as your initial data of the Minkowski problem. And now you try to extend the problem in the Minkowski signature, but the way you extend this is just by looking at how the iconal equations look in Minkowski signature. And what you realize is that actually the iconal equations are very simple. The Euclidean vectors A and B combine themselves into a null vector B, which is null, of course, and the iconal equations then tells you how to propagate that data, and that data propagates ballistically. So basically all the data here, you just have a bunch of null vectors, and those null vectors are constant along the directions of themselves, like parallel transporting along all the Minkowski space. So this is the prescription. It's an extremely simple problem. So there are some consequences for this problem. So that means that this relation, which the one that I gave you like a motivation or the definition of the local temp or the entanglement temperature, sorry. Previously this was called local temperature. That's why I probably will be calling them indistinguishably these two terms, these two names. But then actually this relation can be covariantized in this other relation. So actually the object that is covariant and that is going to play a role in the Minkowski signature is going to be a entanglement vector. And that entanglement vector is proportional to the momentum, which in this particular high energy limit is just a null vector. And the coefficient of proportionality between temperature and momentum is precisely the relative entropy, which is a scalar and well-defined quantity. So this is the upgrade of this equation in the Lorentzian, in the Minkowski context, let's say. But let me go back and tell you how how our approximation to the molar Hamiltonian looks like now in terms of this more covariant way of writing things. Okay? So the idea is that you just write down the original formula that I gave you, but now using the fact that you can write everything in terms of scalars and vectors, and then you can write this very nice formula in terms of where these operators again are defined with respect to these null rays, because it's the same creation operator. You create just excitation that defines those are like some sort of null ray operators if you want. Now, written in this form, it is very interesting to write it in this form, because then that gives you the way to define some notion of current. So it seems like now you see the molar Hamiltonian as a conserved charge, as a conserved operator, for which you have also a locally conserved current associated to it. So this is very nice, and of course, this immediately tells you, because this current is conserved by the equations that the relative entropy satisfy, basically the equations that are given by the null propagation, then immediately tells you that there is a current associated to this operator. Later on, this fact is going to be important in a minute. But then the question is, okay, I have told you everything about entanglement temperatures and how this allows us to write down an approximate version of this very important operator that describes the subsystem. But what can we do with this approximation? That's the next question. Okay, we have a very interesting object, very concrete and explicit in the case of free theories and so on, but what type of observable can we compute out of it? And that's where the Rényi entropies come in precisely. So let me come back a little bit to the definition of the Rényi entropies, but let me just rewrite it in terms of partition function, just the trace of e to the minus n h. And let's try to interpret this H molar Hamiltonian as an ordinary Hamiltonian, like in a thermodynamic system. So the Rényi entropy is just given by this, but in particular, in the limit when n goes to 0, this gets simplified, of course, and what you get is that the Rényi entropy is essentially the free energy associated to this system. It's like a free energy thing. And you can see the role that n plays. So basically, n is like is a parameter that it plays the same role as the inverse temperature. So in particular, if you take the high temperature limit of an ordinary system, so the information that you need, or it's going to be enough in this very extreme limit, is to know the Hamiltonian or the structure of the Hamiltonian at very high energies. So the idea precisely is that the n going to 0 limit of these Rényi entropies will be governed by this information that we have, and we will be able to effectively compute those Rényi entropies. So that's the statement. But now, let me go back to field theory, and let me just tell you that in an ordinary thermodynamic system, the free energy, you know already what kind of the answer is. The free energy in a CFT, and the idea is that since we are in the very high energy limit, we can think of like any QFT that are very high energies is described by a CFT, then you can kind of use this type of reasoning. But of course, this is just for a thermal state, an ordinary thermal state. We know that the free energy is proportional to the volume. We know how it scales with the temperature, and we know the proportionality coefficient, which is, in some literature, they call it the Stefan-Boltzmann constant, but this is the coefficient that characterizes the CFT per se. So this is a very universal formula. And so it is very simple to conjecture that for the Rényi entropies in this limit, you will also get something similar. Of course, just by analogy, you can see how it should scale with the object that is playing the role of a temperature. You also propose that it's proportional to the Stefan-Boltzmann constant. But in this case, of course, it's not going to depend on the volume, but there's going to be some geometric dependence. And this is encoded by this function that in principle only depends on the geometry. So all the information about the underlying theory will be encoded here. And this is just a conjecture so far. Okay. So let me just tell you that we were able to prove this conjecture precisely in the case of free theories, again. But not just prove the conjecture, but tell you exactly how to compute this geometric quantity. So this geometric quantity is completely determined by the entanglement temperatures that I've been advertising so far. So if you know all the entanglement temperatures, you just need to do these complicated integrals, and that will give you the geometric dependence of the Rényi entropies for an arbitrary region. Of course, this is just mapping a very complicated problem to another very complicated problem, which is the computation of the Rényi entropies. That is a very interesting relation. And you can just propose that this is going to be true for an arbitrary CFTs. And we are going to see that at least there are some indications that this is the case in 2 dimensions. Okay, we check these formulas. Again, there are very few explicit computations of Rényi entropies, so we check in every single case in which the Rényi entropies are known, and in every single case in which we know how to compute the local temperatures, or entanglement temperatures, sorry. And then, so we check against the spheres, we check it against multiple intervals, and we check it against the strip, and everything matches perfectly. Let me just tell you that for the strip, this is the geometry of the strip. These are like the directions of in which we are perturbing the state. So the entanglement temperatures are highly non-trivial. They are defined by pieces. So this match is really non-trivial, the match that I'm just telling you, in this particular case. In the other cases, basically, you can argue that it's dictated by symmetry and so on. Okay, so what I would like to do next is just to try to tell you a little bit about what can we learn about these quantities in the context of holography. But before that, let me mention something about the Rényi entropies. I told you, I mean, the equation that I wrote here are, once again, restricted to the t equals 0 slice, because that's that's how we wrote down these formulas. But it's very easy, since we already did the work previously, it's very easy to extend these formulas for any arbitrary surface homologous to A, and the extension goes basically along the same lines that the extension that I described before. So basically, the reason is that all these local temperatures are constant along these null rays, and you can construct a vector field which is conserved and so on. So everything follows. But now this current is not anymore an operator, but it's an actual current. It's a function, I mean. And similarly, so this is the explicit form of the current, whose flux will compute the Rényi entropy. So you can think of this Rényi entropy as a thermodynamic entropy, and this current as some sort of thermal entropy, some thermal current, entropy current, sorry, some sort of entropy current, whose flux will give us the total entropy of the system, if you want. But you not only get a current, but you also get an energy momentum tensor associated to that state. So that makes this a very interesting description. So basically, just by playing with these quantities, you are actually getting some kind of hydrodynamic description of this very high temperature state, which entropy is giving you the Rényi entropies. So this is kind of the description, and that description is the one that is going to be very useful in translating what I have told you so far into the holographic context. So in holography, there is a very well-known prescription of how to compute Rényi entropies for theories which have holographic duals. And this is, it was introduced by Dom. Basically, what you do is you have a region in the boundary, and you ask, this minimization is wrong, you ask for the solutions to a cosmic brane which which is anchored at the boundaries of the boundary region. It has a particular tension, so you have to solve the nonlinear Einstein's equations coupled to this to this energy brane, and then you find the solution which asymptoted, which has the right boundary conditions at infinity, let's say. And the Rényi entropy, or this quantity that I wrote with the twiddle up, is going to be the area of such cosmic brane. That's the prescription given by Dom. Sorry. Now let me just tell you that Dom gives us a prescription for the twiddle Rényi entropy, which is actually just some combinations that you can obtain from the Rényi entropy. But the interesting thing is that this twiddle quantity is actually the one which is associated to the von Neumann entropy associated to the state rho to the n. So this guy that I wrote here. So this state, the entropy of that state is n twiddle. So this is a very nice connection, because you know that essentially from the previous slides, from the field theory computation, we also know how to compute, when n is small, the energy momentum tensor associated to that state. So now what we are going to do is to use this as an extra boundary data, and try to solve explicitly for the cosmic brane in a particular setup. So, and again, the simplest setup that we can explore these ideas is in 2 dimensions, because the formulas are quite explicit and well known. So again, the input is, we're going to use the energy momentum tensor that we obtained from the formulas that I showed you at the beginning, that is determined from the local temperatures. Since the local temperatures are universal, we expect this energy momentum tensor to also be universal and describe this boundary state. It turns out that in 2 dimensions, the gravitational problem has been solved long ago. So basically, if you know the boundary energy momentum tensor and the metric at the boundary, you know exactly what should be the metric which is dual to that, which has these boundary conditions at infinity. And this is given by Bañados in 1999. So this is great, because now we can just analyze this metric for the particular boundary energy momentum tensor that I described for you. And let me just start with the simplest case, and I will end very quickly after that. So the simplest case is Rindler. So Rindler is just, again, half line in the 2-dimensional case. So the metric has this form, and one of the features that have the Bañados solution is that the Bañados solution at some point, they cut off. So there is a cutoff in which the solution, after certain surface, it stops being valid. So you have to do more in order to complete the full gravitational solution. But luckily for us, in the particular case of Rinder, this cut off exactly where it should cut off. Because precisely the surface where this solution breaks down, is when the determinant of this metric becomes 0. And that happens when this is the holographic coordinate. Z are just the complex coordinates that parameterize the boundary. So this thing precisely cut off at a cone, which are given by zeta equal to r. But this cone is actually, how do you say that? It's actually singular. In other words, it's not a two-dimensional surface. If you look the induced metric on that cone, you get that it's just one-dimensional. In other words, if you take the circles, you see that the length of these circles that are induced by the boundary circles that are given by the current, the boundary current, those circles have length 0. So essentially, even though it looks like a cone, in reality it's just a brane. And this is precisely the Dong's brane. And when you look at the conical deficit associated to that brane, you find that it's precisely the one given by Dong. So essentially, we have the metric, we obtain the metric just by solving Einstein's equation, and we find the brane that Dong proposes as the appropriate solution. And we can compute the area of that brane, and we find that it actually agrees with what we expect. So we get the Rényi entropy right. Okay. So this probably is not so surprising because of the symmetries of the problem and so on. But I guess the less trivial case is an arbitrary number of intervals. You can just repeat the same exercise, and I have 0 minutes. So you can repeat the same exercise for an arbitrary number of intervals, and everything goes through. So you, again, look at the surface of 0 determinant, and you look at what happened in that surface. In that particular case, the metric induced on that surface is not one-dimensional, it's two-dimensional, but the important thing is that at n, in the limit n going to 0, at this point, the n going to 0 limit is actually going to matter. In the n going to 0 limit, this part of the metric is basically relevant, and it effectively just becomes one-dimensional. So once again, you get this type of argument. Just to illustrate this, and this is, the idea is the following. You have two intervals, you have this fluid on the boundary, the Bagnado solution tells you that the solution is okay up to this pillow region, and on that pillow region, what you see is that in the n going to 0 limit, these circles actually have 0 length. So what you get are actually these two lines that crosses the 2 points. So essentially, the brane actually becomes singular and is unique. If you remember from entanglement entropy analysis, you have these two possible solutions that is connected, that you can connect the intervals in different ways. So in the end, going to one limit, what we are discovering from these solutions is that these two possible saddles actually converges into a single saddle, and then the brane actually intersects each other. So this is something very interesting. You can compute the area and you get the right result. So this is what I wanted to tell you about holography, and let me just end here with the summary and future work.
Questions?
Yes.
So you were a bit quick on the holographic computation. So
yes.
What's the check on the multi-interval case? I thought that in multi-interval we generally don't know what the formula should be.
No, but the whole point is that we know what the Rényi entropies are from the field theory side because of what I argued at the beginning. We just use the local temperatures to compute the Rényi entropies because of this formula. So we know these logs. So basically it agrees with so it's a very universal thing. This is kind of interesting. So the Rényi entropies in field theory are highly non-universal, but in the limit when n goes to 0, they become universal and they have this scaling thing. So what we check is that actually from doing this holographic computation, we obtain what we know from the field theory. So that's the check. Sorry. Yeah, I went too fast on that. So.
So just to make sure I understand, you're saying that there is a universality of the n goes to 0 limit of the Rényi entropies. So for example, if I take just a simple holographic calculation of the Rényi entropy, and I don't know, I add like Gauss-Bonnet or something like that, when I send n to 0, I should get the same as without the correction, like without higher curvature?
I would say yes. But these higher corrections are, yes. I would say yes. You should get the same. Yes, all the dependence will be in sigma. Yes, maybe, but the structure will be the same. All the dependence on the field theory will come from the Stefan Boltzmann coefficients. So maybe you will have something that has the same structure that comes from the higher curvature terms, but then, they will have the same functional. They may be correct sigma, as Mark said. Yeah. That would be the idea. So the form of the solution is universal, if you want.
So I'm not sure if you actually explained this earlier, but what is the quantum information meaning of the Rényis at n equal to 0? Like, what is it measuring? I mean,
basically, it gives you all the information that not all the information, but gives you information about the distribution of the small eigenvalues of the density matrix.
I see.
So the density matrix, you can say how it behaves. Yes, it's just that, yes. The distribution of the small eigenvalue distribution of the reduced state on that particular region can be obtained from the Rényi entropies when n is small. That's the idea.
I see. Maybe just one more comment on this multi-interval formula.
This one?
Yeah, you can get the for free fermions. You can get the exact answer for multiple intervals.
Yeah, this is exactly the same one that free fermions.
Right, and there's a kind of trick in which you can view the n interval problem for the for one fermion. Mm-hmm. You can orbifold the path integral that computes the density matrix for n fermions. You can orbifold it so you can view it as n fermions living on one interval.
Yeah.
And is there a sense in which you're using that mapping?
Yeah, I think we use it just to compute this formula. We use this mapping here. Oh. Yeah. I think this is one way of writing that mapping. So essentially here you have n copies. So a single copy of the original plane, the complex plane C, it is covered by n copies of W.
Oh yeah, that's mapping. Yes.
This is the mapping that you use to reinterpret this as n fermions in the particular case of fermion.
I see.
That you did. Yeah.
Okay, thank you. I think we probably better move on. Thank you very much.
Okay, thank you.